Good evening everyone, welcome to Gate Academy and welcome to the first session of our Formulathon series for BARC. I hope everybody is ready, so we'll start. So keep a copy with you so that you can write the formulas with me. Okay, so I will be writing on the board here, so you can write on your papers. Okay, now everything is fine. Yes, we'll start. So regarding BARC exam, so the exam is scheduled right on the first week of April. Okay, we are having right only maximum 10 days remaining. Okay, so हमें prepare करना है. So important part ये last 10 दिन में what is important is हमें formulas याद रखना है, ठीक है, including max. Okay, including max. So mock test start हो चुका है, that is we have already uploaded. So tomorrow you will be able to write it. Okay, tomorrow and day after tomorrow is the timing. So in one sitting आपको लिखना है ना. मॉक टेस्ट दो मॉक टेस्ट रहेगा. फर्स्ट विल बी फ्रॉम 25th स्टार्ट होगा, सेकंड 28 को स्टार्ट होगा, 27 को वी विल बी डिस्कसिंग आवर आंसर्स हियर इन द सेम यूट्यूब चैनल. Okay, yes, good evening everyone. So we'll start. Okay, we are not going to discuss any concept discussion नहीं होगा. Concept के लिए you can see the same channel, right? different videos होगा हमारा ही, ठीक है. Fluid mechanics मैंने 5 sessions लिया था for essential series और different series में I have completed fluid mechanics. Okay, so we'll start with the equations. Remember, so sometimes they may ask based on what. For example, let me start with this. This is your total topics in fluid mechanics, है ना. आप देख सकता है प्रॉपर्टीज ऑफ फ्लूइड्स, फ्लूइड स्टैटिक्स, फ्लूइड काइनेमेटिक्स, फ्लूइड डायनामिक्स, इंटरनल फ्लो, एक्सटर्नल फ्लो, पंप्स एंड फ्लो मीटर, डायमेंशनल एनालिसिस एंड सिमिलिट्यूड. ये हमारा टोटल टॉपिक्स है फ्लूइड मैकेनिक्स में, ठीक है. सो कितने इक्वेशंस आपको याद करना है. मोस्ट ऑफ द टाइम सिंस द एग्जाम इज हैपनिंग आफ्टर गेट के बाद एग्जाम हो रहा है ना, मोस्ट ऑफ द स्टूडेंट्स को याद रहेगा मोस्ट ऑफ द इक्वेशन, ठीक है. सो इट विल बी इजी फॉर यू. ओके, सो with the same order we will continue to write the equation, right? So remembering formulas is very important. Okay, so how can you remember it? That is what I'm teaching. Okay, without seeing the textbook, right, or without seeing your notebook or without seeing your short notes, you should be able to write it continuously from each chapter. Okay, so that is the most important part. I hope it is clear for everyone. Yes, now let us start now. First equation, इस साल क्वेश्चन आया था फॉर एग्जाम्पल आइसोथर्मल कंप्रेसिबिलिटी से बेस्ड एक क्वेश्चन आया था. इफ यू रिमेंबर हाउ वी राइट आइसोथर्मल कंप्रेसिबिलिटी, दैट बेस्ड वन क्वेश्चन विल बी देयर. सो इन द फर्स्ट चैप्टर प्रॉपर्टीज ऑफ फ्लूइड, व्हाट आर द इंपॉर्टेंट प्रॉपर्टी यू हैव? वन इज योर विस्कोसिटी. ऑब्वियसली एवरीबडी विल टेल अबाउट विस्कोसिटी, सबको याद होगा विस्कोसिटी. दूसरा है कंप्रेसिबिलिटी, राइट, दूसरा है कंप्रेसिबिलिटी. सो कंप्रेसिबिलिटी के बारे में व्हेनेवर वी डिस्कस अबाउट कंप्रेसिबिलिटी, आपको ये इक्वेशन ऐसे याद करना है फॉर कंप्रेसिबिलिटी, राइट. मैंने ऑलरेडी बोला है व्हाई डू वी स्टडी कंप्रेसिबिलिटी. कंप्रेसिबिलिटी का हम क्यों पढ़ते हैं? बिकॉज वी वांटेड टू नो हाउ ए फ्लूइड इज बिहेविंग, राइट, विथ रेस्पेक्ट टू द चेंजेस इन टेम्परेचर एंड प्रेशर. मतलब वी वांट टू अंडरस्टैंड द वॉल्यूम चेंज विथ रेस्पेक्ट टू टेम्परेचर एंड प्रेशर, है ना. मतलब इफ वी अप्लाई प्रेशर, वॉल्यूम तो क्या होगा? इफ यू इंक्रीज प्रेशर एट कांस्टेंट टेम्परेचर, प्रेशर इंक्रीज करता है तो वॉल्यूम डिक्रीज हो जाता है. नो प्रॉब्लम, वॉल्यूम विल डिक्रीज, right? So when pressure increases, volume is decreasing, but how much it will decrease, that will be different for different fluid, है ना. मतलब air को आप एक pressure दे रहे हो, the volume change will be different. Water, if you compress water, the volume change will be different. If you compress a different material, it will be different. Okay, so every fluid, that particular the relation will be different. That is not the relation, I can say. Volume change will be different for different fluid. So for that we need a property. Clear? So for that we need a property. So first of all, whenever you are trying to remember compressibility or whenever you start this compressibility, you can write specific volume, right? 1 minute. So specific volume you can write it as a function of temperature comma pressure. Okay, so you should be able to write specific volume as a function of temperature and pressure. Okay, so second step will be what? I'm going to use your max, that is dV is equal to, I'm going to write this equation as partial differentiation of volume with respect to temperature. When I am differentiating with respect to temperature, keep pressure constant, dt plus dou V by dou P into dP at constant temperature. This is the basic equation. This is the basic equation for compressibility. Now, what is isothermal compressibility? Try to write with your, write in your notebook itself, आप भी लिखना है, because otherwise it will be very difficult. Revision is going to continue. The formulas will going to continue. Right? So try to write in your copy as well. So alpha, what is isothermal compressibility? From the word itself, whenever you see in the question paper isothermal compressibility, you need to understand we are keeping temperature constant. Okay? We are keeping temperature constant. So they are talking about volume change with respect to pressure at constant temperature. Why? Because it is isothermal compressibility. Okay? So your equation will be, there is a 1 by V will be there. So 1 by V into dou V by dou P at constant temperature. This is your isothermal compressibility, but your equation does not end because when pressure increases, volume is decreasing. So there should be a negative sign. So minus 1 by V into dou V by dou P at constant temperature. Okay. So I hope you can easily write it. So once again, I will write it. What is the value of alpha? Isothermal compressibility is minus 1 by V into dou V by dou P at constant temperature. Now, मैंने already बोल दिया isothermal compressibility, volume change with respect to pressure at constant temperature. इसका opposite क्या होगा? Opposite of this will be beta, which will be, आप देख सकते हैं यहाँ पे, instead of pressure, I am making it as what? Temperature at constant pressure multiplied by 1 by V. So this beta is what? Beta is your coefficient of volume expansion. This same beta we are using in what? Your heat transfer also. In which process? Natural convection. Okay. In natural convection, we have beta. Okay. Coefficient of volume expansion. So these two things, if you substitute here, you will be getting what? You can say, if I divide this equation by V, I can say this term is nothing but your beta dt minus alpha dp. So this is the basic equation you need to remember first in fluid mechanics. I hope it is clear for everyone. Okay. So this is the basic equation you need to remember whenever we start fluid mechanics. Now, iske basis pe, there was a question this year. They have given isothermal compressibility and they have given some entropy thing. That was a question in what? Thermodynamics this year gate. Okay, connecting question. Though your answer was 0 or something. Okay, so same way we are starting the remaining part. So this is our starting fluid mechanics. Now what is important for us? In fluid mechanics, we don't use isothermal compressibility. We normally use what? We use bulk modulus of elasticity, which is 1 divided by alpha. Okay, so remember alpha's equation, automatically you will get bulk modulus of elasticity. So this is your bulk modulus. This is the equation for bulk modulus. So remember this. So this is our first equation. Okay, this is our first equation to remember. So those who are watching, you can take a screenshot. Okay, so if you want to remember it again and again. So this is our first equation. First set of equation बोल सकता ना, ठीक है? Next क्या है? What is the next part? Obviously, second property we are discussing will be your viscosity. Okay, so the next is viscosity. Next topic is viscosity. Viscosity mein what is the important equation we have? We have Newton's law of viscosity, which is tau is equal to, I can say, mu into du by dy. This is one most important equation for us. Now, if they are asking you to find shear force, your shear force is equal to tau into A. So mu into A into du by dy. Now, what is the unit of viscosity? Viscosity's unit is Pascal second or poise or centipoise, anything. So remember the value of viscosity of water at 20 degrees Celsius. Viscosity of water at 20 degrees Celsius is 1 centipoise, or it is equal to 10 power minus 3 Pascal second. Okay, so based on this, they can ask you, right? So we have done so many PYQ based on this already, है ना? बहुत सारे PYQ हमने किया है इसी टॉपिक के ऊपर. I hope it is clear. Now, shear stress हो गया. Now same thing, whenever we discuss shear stress, आपको transport properties याद होना चाहिए, है ना? Whenever we discuss shear stress, you should remember your transport property. So what are the transport property? Whenever we write transport property, we will write what? Momentum flux. So what is the difference between momentum flux and shear stress? Momentum flux, we will write it as tau yx, where momentum is transferred in the y direction, or we can say minus y direction when we have a flow in x direction. So tau yx, we can write it as minus mu into, I'm saying dv by dy, where we can say, if you want to understand momentum flux, this is the meaning, momentum flux. Okay, so if you want to keep it as u, no problem. Okay, it is like u plus du u, or v plus dv, doesn't matter. Okay, now what is the direction of flow? X direction. What is the direction of momentum? Momentum is transferring from higher velocity to lower velocity. That's why we are using a negative sign. Okay, same way, you have three equations in heat transfer. Heat flux, Q is equal to minus K into dt by dx, which is the law, Fourier's law of heat conduction. Same way in mass transfer, JA is equal to minus DAB into, we can say, DCA divided by DZ. Okay, so easy. Now, in both the cases, all the cases, we can say, what is DAB? DAB is our diffusivity, right? DAB is our diffusivity, right? Same way, what is K? K is not diffusivity. K is what? It is our thermal conductivity, right? What is mu? Mu is our viscosity. It is not diffusivity. So to change this equation, so we can say tau yx is equal to, I am going to change this equation as minus nu into d by dy of rho into u. So what is this nu? Nu is our kinematic viscosity, which is mu divided by rho. Okay, this is nu is our kinematic viscosity. So let me write it in clear. So those who are having confusion, we can write it. Kinematic viscosity, or kinematic viscosity, or this is also known as momentum diffusivity. Momentum diffusivity, kinematic viscosity or momentum diffusivity, which is denoted by nu. Equation is mu divided by rho. Okay, so physically, what is the significance of this kinematic viscosity? What is the significance of this kinematic viscosity? Right, obvious, because what is the meaning of kinematic viscosity? For example, kinematic viscosity of water will be 1 CST, that is centistokes. We will be denoting kinematic viscosity in centistokes. So kinematic viscosity of water will be 1 CST, whereas what is the CST? It is 10 power minus 6 meter square per second. Where kinematic viscosity of air is 15 CST. So diffusivity of momentum is more in what? Diffusivity of momentum is more in your air. So that is the meaning. So understanding this thing is important. So those who want to write, you can write it. Otherwise, we will be moving forward. So CST is the unit we will be using for what? Kinematic viscosity or momentum diffusivity. So same way, you will be having what? Thermal diffusivity in your heat transfer. Okay, thermal diffusivity will be there in your heat transfer. So this is your momentum diffusivity. So based on these diffusivities, you will be having what? Dimensionless numbers. You have Prandtl number, Lewis number, etc., etc., etc. Right? So you will be having 3 dimensionless number. Right? So in mass transfer, heat transfer and fluid mechanics, connecting these 3, you are having 3 dimensionless number. Okay, in your mass transfer also you will learn this. Okay, so try to remember those things. In your heat transfer, you will use Prandtl number, right? So mass transfer, and again Lewis number is there whenever there is a simultaneous heat and mass transfer is there. When the in your humidification part, okay, you use Lewis number. ठीक है? So all things आपके mind पे आना चाहिए whenever we discuss these things. So this is your transport properties. Okay, so ये आपका है transport property. Now viscosity, how viscosity changes with temperature. For gases, viscosity increases with temperature. For liquids, viscosity decreases with temperature. So these things remember in your mind. Okay, I hope you understood. So these are the topics we need to discuss in the first chapter, properties. Now properties में last point होगा, right? In your properties chapter, the last point is Newtonian, non-Newtonian fluids. So graph तो आपको पता ही है. That is, so even though it's a formulation series, ये graph याद रखना है आपको. The graph is between tau versus du by dy. What is du by dy? Du by dy. Every year there will be one question. Last year 2021 BARC में भी एक question था based on these graphs. Okay, so आप लोग को लगेंगे like everybody know this graph. No, everybody don't know this graph. Okay, so always remember. So there will be always one question from this as well. Now, if the relation between tau and du by dy is linear, then it is a Newtonian fluid. Okay, so then it is a Newtonian fluid. I'm not writing it. I hope you know already. Now, we have a term. We have a. This is your Bingham plastic. So this length we can say this is tau naught. So generally, what is the Newtonian fluid equation? Tau is equal to mu into du by dy. This is for Newtonian fluid. Tau is equal to tau naught plus B into du by dy, or you can say it is mu also, no problem. So this is the equation for what? Bingham plastics or Bingham fluids. This is for Bingham. ये है आपके Newtonian. Okay, this will be your Newtonian, and so this is, I am writing it as Bingham. Okay, Bingham, Newtonian. Now you have two power law fluids, है ना? आपके पास two power law fluids है. Power law fluid का importance क्या है? That follow this equation, power law, that is B into du by dy power n, where your relationship is not linear, or we can say we have a apparent viscosity. That is, we have an apparent viscosity term. What is the meaning of apparent viscosity? Apparent viscosity is there. Always remember apparent viscosity term है ना. हमारे ये जो ग्राफ में apparent viscosity आता है only in case of dilatant and pseudoplastic, है ना. dilatant and pseudoplastic में ही आता है. बाकी केस में क्या है? viscosity सेम ही है ना. So उसको apparent viscosity बोलने का कोई जरूरत ही नहीं है, क्योंकि यहां पे आप देख सकते हैं viscosity completely constant है, slope is same. But for dilatant and pseudoplastic, this tau divided by du by dy value is different at different points. When we change the value of tau, du by dy is changing. So when we change these two, the value we are getting is different at different point. So when I substitute this equation here, your equation will become B into du by dy power n minus 1. So always remember, if the n is less than 1 pseudoplastic, greater than 1 dilatant, that you can remember always based on this equation. If the n is less than 1 pseudoplastic, n is greater than 1 dilatant. नॉर्मली एग्जाम्पल बेस्ड क्वेश्चन नहीं आता है, बट स्टिल मैंने आपको दिया भी था मैकैब के नोट्स. इन मैकैब दे हैव गिवन अ टेबल ऑफ एग्जाम्पल, सो दैट इज द स्टैंडर्ड एग्जाम्पल वी टेक. ओके, इंटरनेट में जो भी डिफरेंट एग्जाम्पल देता है ना, वो हम मतलब अप्लाई नहीं कर सकते हर कंडीशन पे. ठीक है, सो सम पीपल विल से ब्लड इज दिस थिंग, paint is that thing, लेकिन you can follow only the example given in MACAB. I have already given that in the Telegram group as well, so please check that. Okay, go through the MACAB. Okay, first chapter में ही है, ठीक है. They have given an example page, so remember that if needed. But normally they don't ask. That is also there. Now, up to this is fine. Now, what is the meaning of apparent viscosity? मैंने बोला है slope, right? Slope is your apparent viscosity. So you can see here the slope is decreasing, right? Your apparent viscosity is decreasing or your slope is decreasing with du by dy or tau. So then it is what? Pseudoplastic. If the slope is increasing, you can see the slope is increasing, right? The slope is increasing, then it is dilatant, right? So always remember this. Apparent viscosity, it is increasing with du by dy, then it is dilatant. Apparent viscosity decreases, then it is pseudoplastic. So always remember the slope, right? Always remember the slope of the diagram, then it will be very, very easy to calculate. Okay, so previously gate mein question aaya tha, so this time, like for example in the BARC exam also, always 10 to 15 mark will be generally from PYQ, right? PYQ from gate ऐसा repeat होता है according to your luck, ठीक है, आपके luck के हिसाब से. So first of all, that's why we say those who are preparing good in gate, most of the time they will get the return in BARC, right? So always remember, so gate preparation always help for this as well. So whenever we draw this diagram, okay, tau versus du by dy, tau versus du by dy. If the question is given as dilatant, okay, if the question is given as dilatant, you can see here, if you want to find the apparent viscosity, what we will do, right? So tau, for this value of tau, what will be the value of du by dy? This will be the value of du by dy. This is the value of tau 1. This is the value of du by dy 1. Now, what is the apparent viscosity here? Apparent viscosity will be tau 1 divided by du by dy 1. Same way, you can calculate at any point, you can find the apparent viscosity. Same way, आपके पास apparent viscosity और du by dy है तो ये दोनों multiply किया तो आपको ये value मिल जाएगा. Slope and this value. ठीक है? So these things you need to remember. Okay? So on any point, right? Any point you should be able to calculate. If you know tau 2 and du by dy, you should be able to find apparent viscosity at this point. Okay, so sometimes if they give you graph and if they are asking some question, graphically solve होना आना चाहिए सबको. Clear? That's why इतना detail मैं बता रहा हूँ. Already gate में इस type का question आया है. ठीक है? So same type question भी आ सकता है. Doesn't matter. And remember, previous year questions available नहीं है, right? BARC previous year questions available नहीं. Most of the questions available now are memory based question, right? So those who have attended previous year, उनके memory से we have taken some questions, right? So most of the time gate का PYQ repeat हुआ है, but we don't know how many questions they have repeated, right? So that is always there. So this is your first chapter, okay? Definitely thixotropic भी है, rheopectic भी है, right? Thixotropic and rheopectic both are there. So remember with thixotropic and rheopectic, both apparent viscosity changes with what? Thixotropic and rheopectic. They are time dependent fluids, okay? Thixotropic, rheopectic are time dependent fluid. मतलब उनके जो apparent viscosity है ना, हम compare कर रहे हैं with respect to time, not with respect to du by dy or tau. Right? Thixotropic and rheopectic are time dependent fluids. Remember it like that. By keeping a constant tau value with respect to time we are analyzing. Okay? With respect to time we are analyzing. So thixotropic, I guess, apparent viscosity decreases with time. Right? Rheopectic increases with time. So I hope first chapter is done with this. Any other doubts in the first chapter? So far in the any other formula you wanted to remember, you can comment. Otherwise, we will go to the second chapter. Yes. Now, so we are moving to the second chapter. Okay, we are moving to the second chapter. That is, what was the second chapter? Let me just show you. So properties of fluids is over. Okay, so with this we are finishing the properties of fluids. We are moving to what? Fluid statics. Fluid statics में क्या है आपके लिए? Like it's very easy equations, right? All equations are very easy in fluid statics. So the first thing in fluid statics is what? First thing in fluid statics is pressure measurement. है ना. प्रेशर मेजरमेंट में क्या है? सो बेसिकली एक ये क्वेश्चन आ सकता है based on this diagram. There can be this one question, that is, what is your absolute pressure? So this is your P absolute, that is here P absolute is 0, that is, or we can say this is your absolute vacuum, 0 Kelvin, right? Absolute vacuum 0 Kelvin. Why absolute vacuum is 0 Kelvin? Why it is not 0 degree Celsius? सोचो, right? So मैंने already 3-4 बार बताया है हर क्लास में, right? So if you understand the answer, you can comment it. Why it is not 0 degree Celsius, right? It is 0 Kelvin actually, no? Absolute vacuum. Why it is not 0 degree Celsius? So I hope everybody is getting the answers. Yes, no, yes, no. Now, this is your PATM. So this distance is your PATM. Now, if we have a point here, the total distance from 0 absolute vacuum is, your absolute pressure. This is your P absolute, right? This total is your P absolute, right? The total is your P absolute, where this is your PATM. So at this point, at point A, what is the pressure at point A? Absolute pressure at point A, P absolute is equal to, it will be your atmospheric pressure plus gauge pressure. Gauge pressure in the sense whichever gauge, with whichever gauge you are measuring the pressure. So this distance is your gauge pressure and this is your atmospheric pressure. You need to add, you will get the total absolute pressure. So we can say the total absolute pressure will be this much distance. Okay, so out of that, this will be your PATM plus P gauge. Now, if it is vacuum, right? If it is vacuum, what is the meaning of vacuum? Vacuum is a very important concept in thermodynamics as well, no? Vacuum. What is the meaning of vacuum? I've created a vacuum inside a room, evacuated container. But I wanted to know what is the meaning of that. Is it absolute vacuum? No. Absolute vacuum meaning is what? The pressure should be 0, right? Pressure should be completely 0. Is it possible to make absolute vacuum? No. Right? It is not possible to make absolute vacuum, but we don't know what is the vacuum, what is the value of pressure there. Because what is the meaning of vacuum? Any pressure below atmospheric pressure is vacuum. What is the value of atmospheric pressure? Let it be, I'm saying 1 atm or 101.3 kilopascal. So any value below this is a vacuum. When we are drinking a juice, right? The pressure we are making in the straw to have a flow is vacuum. But we are not creating absolute vacuum, ना? हम लोग absolute vacuum थोड़ी बना रहा है, right? So we are creating some vacuum which is less than 101.3. That's all. Okay, so this is the simple logic. So any pressure which is less than atmospheric pressure, that value is vacuum. So here what will be the absolute pressure? Absolute pressure will be the distance from absolute vacuum. What will be the vacuum gauge pressure or vacuum pressure? Vacuum pressure will be this distance. This will be your P vacuum. This will be your P absolute. Because whenever we are measuring something, we are using a gauge, no? We are using a vacuum gauge. So that gauge reading, you can say the gauge reading, that is here P vacuum will be equal to what? We can say your P vacuum plus your P absolute will give us total atmospheric pressure, or your vacuum pressure or your absolute pressure will be equal to atmospheric pressure minus vacuum pressure. So no need to remember any formula and all. Remember this diagram. You should be able to solve all the questions. Easy. So understand these things. Then what is the next part? Once this is done, we have a container, any container, simple container. That is, they can ask you to find the pressure at the bottom, B, right? So I am saying here the pressure acting is, if it is an open container, the pressure acting is P ATM, and this is height is H. So any pressure below is equal to, right? Pressure below is equal to pressure above plus rho G H. Here what is the pressure above? It is atmospheric pressure. So P at the bottom is equal to atmospheric pressure plus rho GH. And if they are asking pressure at the bottom in gauge, this will become what? Only rho GH. Why? Because whenever we calculate gauge pressure, your atmospheric pressure value will become 0. Easy? I hope it is clear for everyone. So this is the most important equation for your fluid statics. Okay, so इसको based like same thing, इसके base पे हमें वो क्या है, like based on the same equation you have hydraulic jack, right? Hydraulic jack का function है, for example hydraulic jack का equation है, for example like this. You have hydraulic jack like this. This is hydraulic jack, for example. That is here the force acting here, that is this entire thing is filled with fluid. Okay, so here the force acting is F1. Okay, so the area is A1, so here the force will be F2, area is A2. So if we use a very small pressure here, that is F1 by A1, same pressure will be happening in the same horizontal direction. That is, in static fluid, pressure will not change in horizontal direction. So if we have a static fluid, pressure at this point 1 and pressure at this point 2 will be same. That is, what we are saying is here pressure at point 1 it will be equal to pressure at point 2. That is, we can write F1 by A1 is equal to F2 by A2, or by using this we can write F2 by F1 is equal to A2 by A1. So what is F? M into G, right? M into G. So based on that you can write it. What is F2? F2 I can write M2 into G mass. F1 I can write M1 into G. So by using an area ratio of 100, by using a 10 kg weight, you will be able to lift a 1000 kg car. Okay, so that is the meaning. Easy. So based on this, they can ask question. So understand statics. That is, in horizontal direction, your pressure will not change in static. In vertical direction, pressure will change. इसलिए सबको ये problem होता है. For example, simple thing, right? सब लोग हमेशा ये पूछता है, sir, pressure is force by area है ना, pressure is force by area. So why in Bernoulli equation we are not saying like area is increasing? Now why it is the pressure is not changing? Like for example, ये ऐसे doubt आता है students को, like for example normal doubt is like this, है ना, यहाँ पे normally pressure कहाँ पे ज़्यादा होगा? Obviously हमारा second point पे pressure ज़्यादा होगा, है ना, second point पे pressure ज़्यादा होगा. So the students' question will be normally like this, sir, here area is increasing, so pressure should decrease there, ना? Because we say your pressure is equal to, है ना, normally ये basic question है, सबको होता है ना, F by A होता है, ठीक है? So यहाँ पे area increase हो रहा है. So why when area is increasing pressure should decrease, ना? Why it is not same here? Simple logic ये है. We are not talking about statics. We are not talking about statics. Now the fluid is flowing now. So we cannot use the equations we use in statics. Okay, simple meaning like that. Okay, so whenever the liquid is coming in bulk, right? So obviously it will have more energy now, right? ऐसे सोच सकते हैं. Like this, when a river is flowing, that is different. When a tsunami is coming, that will be huge now, huge energy. Same logic. When fluid is flowing, that is a different scenario. Okay, statics is different, kinematics is different, dynamics is different. Kinematics, dynamics we will discuss when we discuss fluid flow. Okay, so those things are important. I hope that is also clear. Now then, manometer है, manometer I'm not discussing because already manometer का बहुत सारा कोई इक्वेशन रिमेंबर करने के लिए ही नहीं है, आपको मैनोमीटर सॉल्व करना आना चाहिए बस. Okay, so manometer I am not discussing, that is another topic here. Next topic we have is buoyancy. Next topic we have is buoyancy. For chemical engineering, we have only two basic equations for buoyancy. One is based on Archimedes principle. All equations are based on Archimedes principle. That is, we have two cases basically, okay? Two cases. That is, if we have some body, which is completely immersed in water. Now this body is completely immersed in water, okay? This body is completely immersed in water. This body is completely immersed in water. In that case, what will be the equation of buoyancy? Always your equation of buoyancy is density of the fluid G into volume of the body, right? So that is volume of the submerged body. That is how much volume is immersed in water. That is the meaning, right? Because why it is so? What is the Archimedes principle? Always remember the Archimedes principle, right? What is the value, magnitude of buoyant force? Magnitude of buoyant force is weight of water displaced by the body, weight of fluid displaced by the body. That is, if I jump into water, right? If I jump into water, buoyancy क्या होगा? Buoyancy force on my body क्या होगा? It will be equal to जो भी बाहर आता है ना पानी, उसका weight हमें measure करना है. That is a concept. ठीक है? If I wanted to find what is the buoyancy on this pen, I am putting this in water. So you need to understand, or you need to calculate the weight of water that has come out. Okay? Weight of water that has come out. Now here we want what? We want this complete volume of water because, sorry, complete volume of the body, because the body is completely inside the water, because that much amount of water will come out, ना? है ना? इतना complete body पानी के अंदर है, so हमें volume किसका चाहिए, right? हमें volume चाहिए according to this much. Clear? So your equation will be always density of the fluid G into submerged portion of the body. Right, submerged portion of the body. Now in this case it is completely submerged. So what will be this? This will become volume of the body. Okay, this will become volume of the body. So always remember, this will be always submerged portion of the body. So why we are always writing submerged portion of the body? The reason is, ये case के लिए भी applicable है. This equation is applicable to this case as well as this case. When you have a case like this and your body is like this, so in this case only this much is inside the water. So in case of floating, right, in case of floating, buoyancy is what? Density of the fluid G into submerged portion of the body. So this is your submerged portion. In this case it is completely inside the water, so then we can say what? This will be your total volume of the body, है ना? Total volume of the body. Easy? So these are the equations we have. Now, okay, completely submerged is very easy. Sorry, completely immersed is very easy. Now, in this case, what is the speciality? In this case, what is the speciality? क्योंकि हर बार हमें questions आता है floating के basis पे. Chemical के हमारा सारे question जो होता है ना, floating पे ही आता है. Right, floating in the sense basic floating, that's all. So why it is floating, right? उसके लिए एक reason तो होना चाहिए ना, right? उसके लिए एक reason होना चाहिए. अगर buoyancy ज्यादा है, right? If the buoyancy is more, क्या होगा? ये body पूरा पानी के ऊपर आ जाएगा, है ना? If the buoyancy is more, the body will completely come to the top. If the weight is more, the body will sink. Both are balanced, that's why it is floating. Okay, simple logic. So we can remember like this. Here, in case of floating, okay, in case of floating bodies, why it is floating? Because both are balanced, so we can say what? Weight of the body, density of body, G into volume of the body. Total volume of the body is equal to, this is the weight of the body, it is equal to buoyancy, that is V submerged. So from this, for floating, you will have an equation. Submerged volume divided by total volume is equal to density of the body divided by density of the fluid. Easy? This is enough to solve all the questions. Okay, this is enough to solve all the question. And दूसरा type का question क्या हो सकता है? Second type of question in this chapter, right? Equation तो उतना ही है और कुछ नहीं है. Equation ये question ये हो सकता है resultant force के ऊपर एक question हो सकता है, right? Resultant force के ऊपर मतलब ये तो phone, for example, this is a phone. Now, what are the forces acting on the phone? Downward direction, you have a weight of the phone, gravitational force, no? हाँ, weight of the force, weight of the phone. ऊपर की तरफ air का buoyancy given by the air, no? Okay, so now if I leave the force, if I leave my hand, what will happen? Phone नीचे जाएगा. Why the phone is going down? Because weight of the phone is more compared to the buoyancy given by air. That's why it is going down. Okay, so simple logic. Now, in case of a balloon, ये मेरे पास एक balloon है. Balloon में क्या क्या forces act हो रहा है? Weight of the balloon is going down. Buoyancy given by air is acting in upward direction. So what is the resultant force here? Resultant force will be weight minus buoyancy. So magnitude of this is the resultant force. एक बॉडी के ऊपर जो भी फोर्स होगा, दो फोर्स हो सकता है, एक वेट एंड बायंसी. ये बस ये हमें देखना है इन आवर फ्लूइड मैकेनिक्स. ठीक है, सो वेट होगा, बायंसी होगा. नाउ इंपॉर्टेंट पार्ट, रिजल्टेंट फोर्स कैलकुलेट करने के लिए आपके पास क्वेश्चन आ गया, देन यू कैन यूज दिस वेट माइनस बायंसी. सो अगर वेट से ज्यादा है तो क्या होगा? फोन के केस फोन नीचे जा रहा है. बायंसी से ज्यादा हो तो क्या होगा? बलून के केस. व्हेन आई लीव द बलून, राइट, बलून अगर ऐसे मेरे पास एक बलून है, इफ आई लीव इट क्या होगा? वो ऊपर जाएगा ना. व्हाई? बिकॉज बायंसी इज मोर कंपेयर टू द वेट ऑफ बलून. इसलिए बलून के अंदर क्या फिल कर रहा है? हीलियम फिल कर रहा है, हाइड्रोजन फिल कर रहा है ना, हीलियम और हाइड्रोजन. व्हाई? बिकॉज इट इज डेंसिटी इज लेस. क्लियर? सो व्हेन आई लीव इट, बायंसी विल बिकम मोर कंपेयर टू weight of the balloon. Easy. So this is the second part. This is the last part in our statics. So that is the end of your statics. So we have done both properties of fluids and fluid statics. Done for everyone. Kinematics. We will go for kinematics now. Up to this, I hope everybody is fine. Yes, no, yes, no. Yes. Next is kinematics. Kinematics में हमें क्या क्या है? दो equations रहता है, major equation. One is what? Velocity is equal to, we will represent it as ui plus vj plus w के एक equation होता है ना. Acceleration के लिए equation क्या है? What is the equation for acceleration? Whatever, if you want to find the magnitude of acceleration, we will write in terms of what? ax, ay, az. है ना, acceleration in x direction, y direction, z direction. So what is the equation for acceleration in x direction? This is very, very important. Acceleration in x direction is velocity in x direction with respect to time. So this is your local acceleration plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. ये इक्वेशन आपको याद होना चाहिए क्योंकि ये इक्वेशन हम यूज करेंगे इन आवर नेवियर-स्टोक्स इक्वेशन एज वेल. सो ay इज dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. So try to write it and remember the equation. Az is equal to dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. So ये आपका है complete equation for acceleration. Now acceleration equation में आप देख सकते हैं, that is first three terms 1 2 3 represent your local acceleration. Local acceleration in the sense what? Your velocity change with respect to time. Steady flow के लिए ये तीनों वैल्यू 0 हो जाएगा, right? Steady flow के लिए तीनों वैल्यू 0 हो जाएगा. Now the second term is your convective acceleration. So they can ask the question. Okay, so this equations are very important. Next question. Yes. Next question. Not next question, next topic. So once acceleration is done, next equation you need to remember is continuity equation. What is a continuity equation? You know, simple continuity equation, everybody know, that is mass flow rate is equal to density into area into velocity. So for steady flow, mass flow rate is constant if you have one inlet, one outlet. Now, general differential equation of continuity is this: density change with respect to time plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. This is your differential equation of continuity. In this, if it is a steady incompressible flow, if it is a steady incompressible flow, steady flow means क्या हो जाएगा? Steady flow में d rho by dt cancel हो जाएगा, ठीक है? d rho by dt will be cancelled in case of a steady flow. Now incompressible in the sense what? आपका density constant हो जाएगा, है ना? Density will be constant. Now you can say for steady incompressible flow, dou u by dou x plus dou v by dou y plus dou w by dou z will be equal to 0. ये है फाइनल इक्वेशन. इससे क्वेश्चन आ सकता है ना? इजी है. So these are the equations we need. इतना काफी है for BARC mostly. After this, if you can remember vorticity, okay, that is curl of V, that is you can remember curl of V equation, or stream function, potential function भी याद रख सकता है, right? Not needed, but still, right? Sometimes if they ask, right? Because PSU exams है, ठीक है? Sometimes they can ask. So stream function, potential function भी याद रख सकता है. Next, right? Next. These are the things for what? Kinematics. Kinematics में generally gate में हम इतना यहाँ तक ही जाते हैं, ठीक है? Sometimes in BARC they can ask from rotational flow, that is curl of V use करके question आ सकता है. Remember that. Now, dynamics. Next part is what? Dynamics. So we are doing a quick formula series now. So dynamics में सबसे important क्या है? सबसे important है Bernoulli equation. तीनों form of Bernoulli equation is very important. That is P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. So this form of the equation is your Bernoulli equation, where what is P1 by rho? It is your flow energy per unit mass, kinetic energy per unit mass, potential energy per unit mass. Okay, so whenever I'm writing the equation in terms of height or head, P1 by rho g plus P1 square by 2g plus Z2 is equal to P2 by rho g plus V2 square by 2g plus Z2. Last equation in terms of pressure, P1 plus rho V1 square by 2 plus rho g, यहाँ क्यों Z1, ये Z1 होगा ना, ठीक है, rho g Z1 is equal to P2 plus rho V2 square by 2 plus rho g Z2. ये हो गया आपका टोटल बर्नौली इक्वेशन, है ना? सो बर्नौली इक्वेशन में क्या क्या लिमिटेशंस है बर्नौली इक्वेशंस का? समटाइम्स दे कैन आस्क दिस. ओके, बर्नौली इक्वेशंस. ओके, स्मार्ट लर्नर इज आस्किंग सर असम्पशंस, कौन से असम्पशंस? अभी देख रहा हूं मैं आपका कमेंट. सो विच असम्पशंस आपको चाहिए, लाइक for which equation? So but if you want me to tell the limitations, okay, limitations, I was telling about limitations ना. Limitations क्या क्या है? First of all, incompressible होना चाहिए, steady flow होना चाहिए, है ना? Obviously heating and cooling effects नहीं होना चाहिए throughout the flow, है ना? We are applying Bernoulli equation on a same streamline at two different points, and always remember frictional losses should be negligible. That's why हम हमेशा Bernoulli equation center line पे apply करते हैं, ठीक है? Then only it will become more approximate, right? We are doing an approximate calculation ना. Bernoulli equation से जो velocity हमें मिलेगा, that is maximum velocity, है ना. Actual velocity will be different because we are approximating things by using Bernoulli equation. हमारे convenience के लिए हम point select करते हैं, right? It is not the actual value, obviously. Okay, so this is very important. So always remember, steady होना चाहिए, steady incompressible होना चाहिए. Okay, so these things are very very important. Now heating and cooling section क्यों नहीं होना चाहिए in Bernoulli equation streamline? Because whenever there is a heating and cooling section, density will change, so incompressible assumption will go off. Okay, so those things you need to remember. Now whenever we consider friction, here we will be having what? Here we will have a term of GHF for friction. Here you will have a term of HF. Here we will have a term of rho GHF whenever we consider friction. Okay, so whenever we consider friction in the Bernoulli equation, we will add a GHF term, HF term, rho GHF. Whenever you have a pipe flow, we are interested to calculate what? This rho GHF or HF, head loss due to friction. What is the meaning of head loss? Right, it is the additional height that we need to give by a pump, so that we need to avoid the complete pressure drop. Okay, हमें एक पर्टिकुलर पॉइंट से दूसरे पर्टिकुलर पॉइंट तक फ्लो कराना है, सो पंप के थ्रू कितना एनर्जी चाहिए ना, दैट विल बी डिसाइडेड बाय व्हाट? द फ्रिक्शनल लॉसेस. ओके, सो नाउ व्हेन वी गो फॉरवर्ड, फ्रिक्शनल, अभी तो हम सिर्फ फ्रिक्शनल लॉसेस कंसीडर कर रहे हैं ना, और भी लॉसेस हो सकता है, राइट? ऑल द अदर लॉसेस, ऑल द माइनर लॉसेस वी विल ऐड इन द राइट हैंड साइड. Okay, all the minor losses we will add in the right hand side. So this is our Bernoulli equation. So Bernoulli equation based question आ सकता है BARC में. That is Bernoulli equation based previously आया है. Okay, so whenever you apply Bernoulli equation, क्या क्या remember करना है आपको? Right, whenever we apply Bernoulli equation, what are the things you need to remember? Whenever we use Bernoulli equation, there are some rules. One first rule is what? Whenever we select point, right? Whenever we select point, one point will be selected based on the question. Second point will be selected based on the data, given data. Okay. So whenever we select reference line, select the bottommost line. Okay. And whenever we say surface of one fluid, right? Like free surface velocity, you can take it as 0. Okay, and apply, always take a streamline in the center of the pipe. Okay, so these are some rules, so you can remember that. So this is your Bernoulli equation. Now, once the Bernoulli equation is done, we'll move to what? Directly we can move to internal flow. Yes. So Bernoulli equation based, Bernoulli equation में और कुछ equation तो ही नहीं है. It's very simple. Now, yes, some people may ask about kinetic energy correction factor, that we will discuss in the internal flow chapter. Okay, no problem. Now internal flow, what is the meaning of internal flow? Internal flow meaning is, we are going to discuss about pipe, where the entire flow is confined by the solid surfaces. Entire flow is confined by the solid surfaces. That is, from inlet to outlet, the complete flow. We are interested only when the pipe, when the fluid enters this inlet of the pipe at point 1, and at the exit of the pipe point 2. This is our interest. Now, Reynolds number. What is the meaning of Reynolds number? Reynolds number, rho d v by mu. So whenever we use Reynolds number calculation for non-circular flow section, right? Non-circular flow section, we have to find the equivalent diameter or hydraulic diameter, which is 4 into flow area divided by wetted perimeter. 4 into flow area divided by wetted perimeter. In case of a pipe, right? In case of a pipe, this dH will be equal to diameter, dia of pipe. Then you have what? In case of square duct, it will be same. If it is what? Rectangular duct. If it is a rectangular duct like this. If it is a rectangular duct like this. This is a non-circular flow section, and this is A, this is B. Now, your hydraulic diameter, always remember your hydraulic diameter is 4 times hydraulic radius. Because आपके question में they can ask you hydraulic radius, sometimes they can ask you hydraulic diameter. So question ठीक से पढ़ना है, that is diameter है तो equation different होगा, radius है तो different होगा. It is not divided by 2 or multiplied by 2, ऐसा मत करना, ठीक है. So this 4 is the equation, 4 into hydraulic radius, ठीक है. So radius है या diameter है हमेशा आपको चेक करना है before answering. Yes, next is, so okay, what is hydraulic diameter here? For rectangular duct, 4 into what is the flow area? AB. What is the perimeter which is becoming wet? 1, 2, 3, 4. So it will be 2 into A plus B. Okay. Now for annulus, what is the meaning of annulus? Annulus. This is the annulus, no? Now, in case of annulus, so this is your annulus. What is the hydraulic diameter of annulus? So they can ask you question based on this. Annulus. So annulus, whenever there is a flow through the annulus, these are the two surfaces which is in contact with the fluid. These are the two surfaces which is in contact with the fluid. So we are saying this diameter is D naught and this diameter is DI. Sorry, this is DI. क्या है DI and D naught? So this is your outer diameter of inner pipe and this will be your inner diameter of outer pipe. So which value will be more obvious है? DI से ज़्यादा होगा, है ना? वो outer pipe का diameter है ना, ठीक है? So it will be inner dia of outer pipe. So if I say flow area is pi by 4 into DI square minus D naught square. Okay, so this is the flow area across annulus. What is the meaning of pi by 4 into D naught square and D naught square? So pi by 4 into DI square is this complete area. Pi by 4 into DI square is this complete area. Minus D naught square, what is the value? What is the meaning? So we are getting this area. Okay, so now we are talking about only this area. That is only the flow area for annulus. So this is the flow area for annulus. What is the perimeter? That is pi into DI plus D naught. This is the equation. So this is multiplied by 4. So you will be getting what? DI minus D naught will be the hydraulic diameter for annulus. Okay, so this is the hydraulic diameter for annulus for pressure drop. Obviously, हम fluid mechanics का discuss कर रहे हैं, है ना? Fluid mechanics में your hydraulic diameter for annulus, you can write it. Hydraulic diameter or equivalent diameter or equivalent dia for pressure drop. Annulus. In case of pressure drop is DI minus D naught. Easier. Sometimes लेकिन they can ask for what? Heat transfer. In case of heat transfer. In case of heat transfer, what is the difference? In case of heat transfer, what is the difference in annulus? Equivalent diameter में क्या change हो सकता है? Change ये होगा, आप देख लो. In case of heat transfer, this is the change because your outer surface of a heat exchanger is always insulated. Okay, your outer surface of heat exchanger हमेशा क्या होगा? Insulate होगा ना? Why? Because heat transfer कहाँ पे होना चाहिए? Fluid के बीच में होना चाहिए ना? Fluid और outside air के बीच में तो नहीं होना चाहिए. In heat exchanger, we want the heat transfer only between what? Fluids. We don't want the heat to go outside, right? Otherwise क्या मतलब है heat exchanger का? है ना? So simple. So we don't want the heat to go outside in a heat exchanger. So what we can say is, in case of heat transfer, in case of heat exchanger or heat transfer, this outer surface is not taking part in heat transfer. This outer surface is not taking part in heat transfer. So here, right here the term di will not be there in case of second case you will not have the term di. So your equation will be what? Your equation will be pi, that thing will be cancelled out. Di square minus, your equation will become di square minus d naught square divided by d naught. I hope this is the equation. Any doubt in this means? Otherwise we will move forward. Completed. So in case of heat transfer this is the equation, and in case of pressure drop this is the equation. Already 2-3 बार ये question same question आया है, so remember this. Done. I hope everybody is done with this. Now next equations, next set of equations is very important, because in a pipe flow, what is very important is, in a pipe flow, whenever we start pipe flow, what is very important for us? It is our velocity profile. That is, whenever the fluid is coming inside, your initial part, you have an entrance region, you have an entrance region. So this is your entrance region. So once the entrance region is done, in entrance region आपके velocity will be a function of, always remember करना है, r and x, 2-dimensional flow होगा. Now in the fully developed flow region, मतलब fully developed flow मतलब क्या develop हुआ है, क्या fully develop हुआ है ना, वो तो सोचना चाहिए ना आपको, right? Whenever we say fully developed flow, क्या meaning है? What has been fully developed? Okay, why we are calling it as fully developed flow? Because हमारे जो boundary layer है ना, वो develop हुआ है ना, हमारे जो boundary layer है, that is developed, that is fully developed inside the pipe. ठीक है, तो यहां से आपका जो velocity profiles होगा ना, वो same रहेगा throughout. That's why in the fully developed region we say our shear stress is constant throughout, or our wall shear stress is constant throughout the fully developed flow. Inlet पे fully developed flow, inlet that is at the entrance region आपका tau w maximum रहेगा, and it will decrease continually, and in fully developed flow this will become same. Why it is becoming same? क्योंकि यहां से आपका जो velocity profiles होगा ना, fully developed flow में आपके जो velocity profiles होंगे, that will have the same profile. ये same diagram continue होगा throughout, है ना? That's why same diagram continue होगा का meaning क्या है? मतलब we will be using the same average velocity throughout. So from here onwards, fully developed flow, we can say our average velocity is same, because same profile है ना, तो same ही तो होगा. Easy. So our tau w will also be constant. Now in fully developed flow, our velocity profile or velocity is a function of only r direction, है ना? Velocity will change in r direction only. मतलब center पे हमारा maximum होगा if it is a, and here 0 0, laminar turbulent दोनों case में. But in turbulent case definitely your velocity profile will be different. ठीक है? This is the meaning. Fully developed flow speciality is done. Now entrance length का equation क्या है? What is the entrance length LH? It is 0.05 Reynolds number. So if I can divide here by d, or I am multiplying by diameter here. So this is the entrance length equation for laminar flow. Laminar flow entrance length equation, or entrance length or entry length. So remember this equation as well. Easy. Yes, fully developed flow, everything I hope you understood. Now remember, fully developed flow बेस क्वेश्चन आया था 2021 में, राइट? फुली डेवलप फ्लो टाउ डब्ल्यू कांस्टेंट है करके, ठीक है? तो वो सब आपको रिमेंबर करना है. नाउ नाउ मैंने बोला है दैट इज वी एवरेज कांस्टेंट होगा करके बोला ना, दैट इज वी आर टेकिंग अ वी एवरेज. तो वी एवरेज का इक्वेशन क्या है? हाउ डू यू फाइंड द वैल्यू ऑफ वी एवरेज? जनरली व्हाट इज इक्वेशन फॉर फाइंडिंग वी एवरेज? दैट इज, आपको याद होना चाहिए, मास फ्लो रेट इज इक्वल टू व्हाट? डेंसिटी एरिया वेलोसिटी ना. सो हियर द वेलोसिटी वी यूज इज वी एवरेज. सो एक्चुअली हमारा वेलोसिटी कांस्टेंट तो नहीं है ना, वी आर टेकिंग एन एवरेज. सो व्हेन वी यूज एवरेज के जगह पे इफ वी यूज योर प्रोफाइल, व्हाट विल बी द इक्वेशन? वी कैन से व्हेन वी यूज द इक्वेशन लाइक दिस, आप देख सकते हैं, डेंसिटी एरिया into V average should be equal to integral of 0 to r, मतलब थ्रू आउट द पाइप आपको इंटीग्रेट करना पड़ेगा, डेंसिटी into velocity profile in r direction into your area. Small area will be what? Pi r square का differentiation क्या है? 2 pi r dr. Now rho cancelled out, so average velocity of a pipe of any cross section is equal to 1 divided by a, 2 pi बाहर आ जाएगा, so 2 pi 0 to r u of r into r dr. What is a? Pi r square, so both will be cancelled out, so your equation will be average velocity in a pipe is equal to 2 pi divided by, or this pi r square, है ना, 2 pi divided by pi r square, because a is pi r square, so what will be cancelled out? Pi will get cancelled out, so 2 divided by r square into 0 to r u of r, this is your velocity profile r dr. ये आपका है बेसिक इक्वेशन फॉर वेलोसिटी प्रोफाइल. एनी प्रोफाइल आपको क्वेश्चन में देके दे कैन आस्क यू व्हाट इज एवरेज वेलोसिटी. It can be laminar के लिए तो easy है, right? That is in the laminar case, right? In case of laminar flow, whenever you substitute the velocity profile, you will get what? Average velocity equal to Vmax divided by 2 मिलेगा, ठीक है? If they give you a turbulent velocity profile or any velocity profile, आपको बस इस इक्वेशन में सब्स्टिट्यूट करना है एंड एवरेज वेलोसिटी निकालना है, ठीक है? So this is the point. Yes, so this is the basic equation for average velocity. Now, I hope everybody has written this. Yes, next, entrance और fully developed flow में मैं बोल रहा था. So in your fully developed flow, what is the value of tau? Tau के equation हमने derive किया है. So first equation of tau is r by 2 into minus dp by dl होता है, but we will say del p by l. Now same way, वॉल शियर स्ट्रेस क्या होगा? व्हेन स्मॉल लेटर r इज कैपिटल लेटर r, वी विल कॉल इट एज व्हाट? वॉल शियर स्ट्रेस, है ना? सो ये दोनों इक्वेशंस इंपॉर्टेंट है. नाउ ये सेम इक्वेशन आप देख लो, दोनों डिवाइड कर लो, टाउ डिवाइडेड बाय टाउ w इज इक्वल टू एनी r डिवाइडेड बाय कैपिटल R. ओके, any r divided by capital R. Easy. ये कहां पे यूज होगा? Right. Which where you can use this equation? मैं बस आपको बता देता हूं, like where we are using this equation, because in your gate there is one question is there. So let me just check. बस एक क्वेश्चन मैं दिखा देता हूं आप लोगों को, then we will go. Okay. नॉट क्वेश्चन, हाउ टू सॉल्व, राइट? कैसे सॉल्व करना है मैं एक बार दिखा देता हूं. दैट इज, आप देख सकते हैं. सो दिस इज योर नोट्स फ्रॉम मैकैब में दिया हुआ है. व्हाट आर द एग्जांपल्स फॉर स्यूडोप्लास्टिक, थिक्सोट्रोपिक, न्यूटोनियन एक्सेट्रा, ठीक है? नाउ व्हाट आई वांटेड टू शो इज दिस इज योर डायग्राम फॉर व्हाट, आप देख सकते हैं ऑन बोर्ड. Wait, still coming. Yes. So this is the diagram of laminar flow of Bingham plastic fluid. So ये नोट करके रख दीजिए, नॉर्मली क्वेश्चन आता है. So this is laminar flow of Bingham fluids. Laminar flow of Bingham fluids in a pipe. Laminar flow of Bingham fluids or Bingham plastics in a pipe. Normally हम जो भी करते हैं ना, whatever we discuss in gate is laminar flow of Newtonian fluid. Now this is laminar flow of non-Newtonian fluid, which is Bingham. In this, you can see here you have a plug flow, right? At the center, up to a distance of RC, up to a distance of RC radius, you have a plug flow, then you have a parabolic relation, right? Then you have a parabolic relation. So you can see here, if I draw the shear stress diagram, this will be like this, okay? So you can see here, up to a distance RC, right? Up to a distance RC, your stress is tau naught, that is yield stress. I hope you remember the equation for Bingham plastics. What is the equation for Bingham plastic? Tau is equal to tau naught plus B into du by dy. So question was to find what is the value of tau naught. Okay, what is the value of tau naught? So why I was discussing here is, in Bingham plastics case, in the same equation, you can use the equation, that is when small letter r is equal to RC, what will be the value of tau? Tau will become yield stress. Whenever this will become capital R, this will be tau W. So ये equation आप याद रख सकते हैं, so that you will be able to solve questions. Easy. So this also you can remember whenever we solve questions. Now, coming back, what is the equation for fanning friction factor? What is the equation for fanning friction factor? What is the definition of fanning friction factor? Fanning friction factor. इस साल सबको यही प्रॉब्लम हो गया था, कौन सा फ्रिक्शन फैक्टर दिया है क्वेश्चन पे. सो मैंने ऑलवेज आपको बोला था, जनरली केमिकल में दे विल गिव फैनिंग फ्रिक्शन फैक्टर ओनली, बट this time they forgot to mention which friction factor. Okay, they didn't mention which friction factor, fanning और डार्सी, इसलिए दोनों आंसर दिया है आपके आंसर की में. जो लोग फैनिंग बेस करके करते हैं ना, उनके लिए भी आंसर दिया है इन और न्यूमेरिकल आंसर टाइप रेंज. फैनिंग के लिए भी दिया है, डार्सी के लिए भी दिया है. सो देयर विल बी नो कंफ्यूजन. सो फैनिंग फ्रिक्शन फैक्टर F इज डिफाइंड एज योर टाउ W डिवाइडेड बाय रो V स्क्वायर बाय 2, है ना. Now, what is tau? What is tau W? This equation. So you have another equation for tau W. What is the equation for tau W? Tau W is, I can say, d divided by 4, that is r by 2 is d by 4 into delta p by L. Now, I'm replacing this tau W here. I will get what? If I replace this tau W here, I will be getting the basic equation we use in fluid mechanics. That is, you can see here, delta P is equal to 4FL rho V square divided by 2D. This is your general equation for pressure drop. लैमिनर के लिए भी यूज कर सकता है, टर्बुलेंट के लिए भी यूज कर सकता है, सर्कुलर के लिए यूज कर सकता है, नॉन सर्कुलर फ्लो सेक्शन, एनीथिंग यू कैन यूज दिस. ओके, सो दिस इज द बेसिक इक्वेशन फॉर डेल्टा पी. नाउ डेल्टा पी बाय रो जी इज head loss due to friction, so HF is equal to delta P by rho G, so this will become 4FL rho V square. So obviously rho will cancel out, 2GD. है ना, इजी है. What happens if it is laminar, right? What happens if it is laminar? For laminar flow, what is the change? For laminar flow, if it is a laminar flow, your fanning friction factor is 16 divided by Reynolds number. So if it is 16 divided by Reynolds number, when we substitute, delta P is 32 mu VL divided by D square, or this is also equal to 128 mu QL divided by pi d power 4. So this is your famous Hagen-Poiseuille equation. Now in either, by using any method, you can find what the pumping power required for the fluid, right? How much is the pumping power? Pumping power is calculated based on delta P into Q. So these are the major equations we need for what? total equations we need in pipe flow. Okay, these are the total equations we need for pipe flow. I hope it is clear for everyone. So based on this, they can ask you several questions. So please go through whatever equations we have written so far. Now, laminar flow मैंने बोल दिया, that is friction, fanning friction factor is equal to 16 by RE. Now, what happens if it is a turbulent flow? Right? So remember, for turbulent flow, smooth pipe. What is the meaning of smooth pipe? Right, turbulent flow, smooth pipe. In case of turbulent flow, smooth pipe, you have different equations for fanning friction factor. Fanning friction factor is equal to 0.079 Reynolds number power minus 0.25. ये इक्वेशन आप रिमेंबर कर सकता है. एक और इक्वेशन था, मैं भूल गया. Yes, 0.046. F is equal to 0.046 Reynolds number power minus 0.2. So now क्या है smooth pipe, क्या है rough pipe? What is the meaning of smooth pipe and rough pipe? Why both are different? If it is a rough pipe turbulent flow, F is equal to fanning friction factor will be a function of K by D, comma, Reynolds number. In case of rough pipe turbulent flow. So what is the meaning of rough pipe and smooth pipe? ये भी important है आपके लिए. That is pipe, turbulent flow in pipe. क्या difference है? Because आप देख सकता है, that is in case of this is your roughness in the pipe, right? So मान लो this is your roughness. For example, this is the roughness. Now the laminar viscous sublayer in the turbulent velocity profile. I'm not explaining that again because I've already explained this several times here itself. So if the laminar viscous sublayer, that is the first layer, the laminar viscous sublayer in the turbulent velocity profile is like this, right? So this white line is your laminar sublayer, laminar viscous sublayer. So if your roughness, right, if your roughness is inside the viscous sublayer, then it is a smooth pipe. Okay? Then it is a smooth pipe. If the roughness is coming out of the viscous sublayer, then it will be rough pipe. So in this diagram, this is a smooth pipe. So laminar flow के लिए smooth pipe, rough pipe कोई problem नहीं है. F is equal to 16 by RE है. For turbulent flow, these are the equations. So remember this. So write all these equations. I hope up to this is fine. Yes, no, yes, no. Then we will go forward. Yes, so can we go for the next remaining part? Once the major loss is done, right? Once the major loss is done, we will go for the minor losses. So important equation for minor losses. In case of sudden expansion, what is the equation for H expansion? Remember the H expansion equation. It will be V1 minus V2 whole square divided by 2G. So this is the minor losses equation in case of expansion. So in case of sudden contraction, H contraction is equal to, normally we use this equation, V1 square by 2G into 1 divided by Cc minus 1 whole square, because Cc is your coefficient of contraction. So remember, so this will be your velocity. Remember this, I will represent it as V2. That is the second part velocity. So this already we have discussed. So just remember the equation. So any valve or any contraction or anything, any valve or any equipment, your loss coefficient or loss coefficient will be given in the question. So you can represent the losses like this, KL into V square by 2G. So this is your equation for what? Minor losses. Next part, pipes in series, pipes in parallel. That is another topic we have. Pipes in series, pipes in parallel. If you have different, different pipes in series. Whenever you have pipes in series, like this, length of the pipe L1, L2, L3, diameter is D1, D2, D3. Whenever the pipes is in series, what is the speciality? Remember, your flow rate through the pipes will be same for steady flow. Q1 will be equal to, Q2 will be equal to Q3, that will be equal to Q. So your flow rate will be constant, and what will be different? Your HF total friction will be equal to HF1 in first pipe plus HF2 in second pipe plus HF3 in third pipe. Okay. So this is in case of pipes in series. Pipes in parallel, what is the change? Opposite, right? Flow rate will be added, friction will be same. So this is in the case of pipes in parallel. Now, so once internal flow is done, you have external flow. What is the speciality of external flow? External flow में क्या speciality है? You have a plate in this case. You have a plate. So you have a flow, and you will have a boundary layer formation like this. Okay, so this will be now boundary layer thickness. In case of laminar flow, you need to remember. Turbulent flow, you need to remember. Laminar flow, del is equal to boundary layer thickness equation is 4.91 x divided by Reynolds number x power half. Same way for turbulent flow, what is the equation? I guess this is the equation 0.38 x power, sorry, x divided by Reynolds number x power 1 by 5. So in case of laminar, आप डायरेक्टली ये इक्वेशन भी याद रख सकता है, लैमिनर के लिए डेल इज प्रोपोर्शनल टू x पावर हाफ, टर्बुलेंट के लिए डेल इज प्रोपोर्शनल टू x पावर 0.8. So that will be fine. External flow. Same external flow में they can ask you based on your Navier-Stokes equation. ठीक है, सो Navier-Stokes equation का complete derivation मैंने किया है क्लास में, है ना. So you can remember the final equation at least, because sometimes they can ask you Navier-Stokes equation given in options, right? Given in options. So I'm writing the Navier-Stokes equation in your x direction. That is, your x direction Navier-Stokes equation is minus dou p by dou x plus rho gx plus viscosity mu into dou square u by dou x square plus dou square u divided by dou y square plus dou square u divided by dou z square equal to rho into acceleration in x direction. What is your acceleration in x direction? Convective acceleration plus local acceleration. वहां पे पूरा I'm not writing because already मैंने लिखा है, right? Just now acceleration in x y z direction I have written. Same way in y direction, what is equation? Dou p by dou y plus rho into gy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square equal to rho into acceleration in y direction. Now, why I'm teaching this? Because हमारा जो BARC mock test है उसमें already मैंने 2 questions डाला है based on Navier-Stokes equation. In case in the BARC if they are asking, it should be helpful. Okay, क्योंकि हमारे like in a MACAB only 2 type of solution is given, right? Only 2 type of problems are also given. So remember this equation. Now, important part is how do you solve question based on Navier-Stokes equation? For example, in your question paper, they have given a covered flow. What is the meaning of covered flow? That is, covered flow is this. This is your covered flow. आप देख सकते हैं. That is, the upper plate is moving with the velocity v and lower plate is stationary. Okay, now your flow is in the x direction, but your velocity is changing in y direction. है ना, आपके flow जो है that is in x direction, है ना, movement is in the x direction ना, लेकिन velocity is changing in the y direction. Now we are writing, right, obviously the flow is in x direction, so we will use the x direction, right, x direction Navier-Stokes equation. Now first of all, we are not considering velocity change in x direction. So first of all, your right hand side will become 0 because velocity is not changing in x direction. So आपका acceleration 0 हो गया. ठीक है? So velocity is only changing in y direction. So there is no need of x and y. Now horizontal flow है. So हमारा जो gravitational force का भी effect नहीं होगा. So your final equation will be, right? Your final equation will be minus dou p by dou x plus mu into, right, x direction और z direction में change नहीं हो रहा है, so you have only what, dou square u divided by dou y square, which is equal to 0 because acceleration is 0 in x direction. Now what is this equation? Mu into dou square u by dou y square, which will be equal to dou p by dou x. This is the governing equation in this covered flow. So this is the governing equation for what is the type of flow? It is known as covered flow. That is when one plate is moving and another plate is stationary. Okay, in case of laminar flow. Now, if you integrate this equation twice, you will get the velocity profile. That is different. I am not doing that. So up to this, you can remember. ठीक है? So in your MACAB after this class, what you can go and check is, in MACAB they have given this case. they have given this case, that is one plate is stationary here, this plate is stationary, and the other plate is moving in the upward direction with a velocity v. Left plate is stationary, right plate is moving up. Then how do they use Navier-Stokes equation? Try to understand that. I have explained you how in this case we use Navier-Stokes equation. Done? Easy? Up to this is fine. Now, this is our external flow. So what are the things left in your syllabus? Let us check. Syllabus left. The topics left we have is external flow is done. Now we have is pumps and flow meters. Pumps and flow meters, basic equations in pumps and flow meters. Pump. What is the speciality in case of a pump? We have centrifugal pump. We have centrifugal pump, and obviously we are having the positive displacement pumps, right? Positive displacement pump. So positive displacement pump and centrifugal pump, what is the basic difference, right? In positive displacement pump, right, we are having what? We need what? Higher, like flow rate to zyada nahi ho sakta. For example, we may get constant flow rate only in case of positive displacement pump, right? That is, this will be particular value, right? But we may get more head. Right, we may get more head in case of what? Your positive displacement pump, but in centrifugal pump we may get what? Higher flow rate as well. So that is also important. So those things you can remember. So for centrifugal pump, application of Bernoulli equation is important. That is whenever we use this case. In case of this is our pump, no? This is our pump, centrifugal pump. Now, major uses, we need to take water from lower reservoir to higher reservoir. So this is your basic case of centrifugal pump. So always remember how to apply Bernoulli in case of a centrifugal pump. P1 by rho g plus V1 square by 2g plus Z1 will be equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF, है ना? Now हमें problem क्या है यहाँ पे? We need to make the flow from low energy to high energy, है ना? So to make this flow, we are supplying some energy by using pump. That energy is represented in this equation by HM. HM is the head developed by the pump, right? HM is the head developed by the pump. Now in case of a horizontal pipe section, in case of a horizontal pipe section के case में, in case of a horizontal pipe section, okay, in case of a horizontal pipe section, this HM will be equal to your frictional losses, है ना? In case of a horizontal pipe section में क्या difference होता है? देख लो, horizontal pipe section, ये आपका horizontal pipe section है. I am taking from point 1 to point 2. Point 1 and point 2, horizontal pipe section. P1, P2, I don't know, whatever is the P1, P2, but velocity is constant, no? At point 1 and 2, we average, so दोनों cancel हो गया. Z1, Z2, what is Z1 and Z2? Same line, Z1, Z2 cancel हो गया. So, whatever is delta P by rho G is what? HF, so HF and HM should be equal in case of horizontal pipe section. Easy. Now, the question will be, what is the efficiency of a centrifugal pump? Efficiency of the centrifugal pump is out of the shaft power given to the pump, because pump is energy absorbing devices, ना? That is whenever we switch on our electric motor, जब भी हम electric motor चलाता है, so electric motor is giving some energy to the pump, right? Out of that, how much that pump is able to transfer to the fluid, that will be your efficiency. So power developed by the pump will be Q into rho G HM. Power developed by the pump will be Q into rho G HM. This is the equation we need to remember. Easy? I hope everybody is writing. Now, next one, NPSH. What is the meaning of NPSH? Equation for NPSH. NPSH available is equal to pump inlet stagnation pressure, that is P by rho G plus V square by 2G, which is at the pump inlet, that is pump inlet stagnation pressure minus vapor pressure head. This is your NPSH. Okay, this is your NPSH. So based on the question given to you, you can, by using Bernoulli, you should be able to write the pump inlet stagnation pressure. Okay, pump inlet stagnation pressure you can write. If you are taking water from a well, right, from a lower reservoir, if you are taking this term, we can write it as what? PATM by rho G, by applying Bernoulli, because already I have solved this, that's why I am writing it. PATM by rho G minus Z2 minus HF, then this term PV by rho G. In our industries or in our plant, right, in our plant, for a like overhead vessel also, right, we have a tank here, right. From the tank also, if you want to pump some fluid, in that case, this Z2 will become plus, right, that Z2 will become plus. So remember that. Easy. So this is your equation for what? NPSH. So always remember, NPSH available should be greater than NPSH required. So NPSH required will be always given by the pump manufacturer, right? We don't know what is the exact pressure, we are having at the eye of the impeller. That we cannot measure. Eye of the impeller, we will have the what? Least pressure, right? Because in the eye of the impeller, you have what? Very less area. So that means you will have highest kinetic energy. Highest kinetic energy means lowest pressure energy. Okay. So we can never measure the pressure at the eye of the impeller. Impeller eye में जो pressure होता है ना, वो एकदम कम होता है, वो हम measure नहीं कर सकते. ठीक है. So by using different experiments, आपके जो manufacturers होता है ना, they will give us what? Required value of NPSH. So before installing the pump, we need to check whether the NPSH available is this or not. Why? Because we need to prevent cavitation, right? We need to prevent cavitation. Karan is asking NPSH required कैसे निकालते हैं? So NPSH required is calculated by the pump manufacturer. So if you remember the working of pump, Karan, है ना? Working of pump आपको याद होगा, that is we are going through what? Increasing area, है ना? Increasing area पे मतलब आपके जो pump का cross section होता है, so वो increasing cross section होता है ना? Increasing cross section. So whenever we have an higher area, राइट, काइनेटिक एनर्जी क्या होगा? कम होगा, प्रेशर इंक्रीज होगा. सेम वे आप सोचो, पंप के आई ऑफ द इंपेलर में आपका एरिया कम होगा, सो मीनिंग इज व्हाट? वहां पे आपका जो काइनेटिक एनर्जी मैक्सिमम होगा, सो प्रेशर एनर्जी सबसे कम होगा. लेकिन पंप इनलेट, पंप के आई ऑफ द इंपेलर प्रेशर वी कैन नॉट मेजर, right? So we don't know what is the exact pressure happening there. So what the manufacturers will do is, they will, by keeping different value of flow rates or different cases, they will study what is the change, right? Then they will fix an NPSH required and they will give it to us. So pump manufacturer give us the NPSH required. Then by using this, we will calculate what? NPSH available. I hope it is clear. So NPSH available is calculated by the user. Now, yes, next, flow meters. Flow meters, basically obstruction flow meters are there, right? Obstruction flow meters. So obstruction flow meters में आता है हमारा Venturi and orifice. Okay, Venturi orifice base पे ही question आता है, right? Simple. So Venturi is there, orifice is there. Venturi or orifice are obstruction flow meters. In that you have a common equation. Q is equal to, how to find flow meter? एरिया ऑफ द ओरिफाइस और एरिया ऑफ द थ्रोट. वेंचुरी मीटर के लिए हम थ्रोट बोलते हैं, ओरिफाइस मीटर के लिए ओ बोलते हैं, राइट? ओरिफाइस. सो एरिया ऑफ द थ्रोट इनटू CD इनटू रूट ऑफ, आई होप यू रिमेंबर द इक्वेशन, 2 delta P इनटू रो इनटू 1 minus बीटा पावर 4 सो आई यूज दिस इक्वेशन नॉर्मली. ओके, अब एरिया के बेसिस पे एक इक्वेशन आता है, वो इक्वेशन भी इफ यू वांट यू कैन रिमेंबर, वर बीटा इज डी बाई डी, स्मॉल लेटर डी डिवाइडेड बाय कैपिटल लेटर डी. ठीक है, सो ऑब्स्ट्रक्शन फ्लो मीटर आपको रिमेंबर करना है बस. ऑब्स्ट्रक्शन फ्लो मीटर का मीनिंग क्या है? हम वी आर क्रिएटिंग एन ऑब्स्ट्रक्शन ना, वी आर creating an obstruction like this, we are creating an obstruction like this in between the flow. So this small diameter is D, this diameter of the pipe is capital letter D. Okay, so area of the orifice or area of the throat is the small letter area wala area, that is pi by 4 into small letter d square. Now always remember orifice meter में जो है, right, orifice meter your pressure drop will be more, right, that is you have more losses because orifice meter, right, orifice meter in case of in case of venturi meter the flow will fully develop after some time, right, the losses is less in venturi meter. Now ड्यू टू दैट, राइट, CD हम क्यों यूज करते हैं? क्योंकि हमें एक्चुअल वैल्यू नहीं होता है ना, राइट. ऑब्वियसली there will be some losses whenever, if you remember the derivation में हमने losses consider नहीं किया था. So to consider to make a correction factor, as a correction factor हमने एक CD यूज किया है so that we will get the actual flow rate. ओके, सो ये CD का जो वैल्यू होता है ना 0.97 समथिंग होता है फॉर एग्जांपल वेंचुरी मीटर, 0.6 समथिंग होता है फॉर ओरिफाइस मीटर. सो उससे आपको याद होना चाहिए ओरिफाइस में लॉसेस ज्यादा होगा. ठीक है, ओरिफाइस में लॉसेस ज्यादा होगा एंड वेंचुरी में लॉसेस कम होगा. ओके, सो दैट आल्सो यू कैन रिमेंबर इन ओरिफाइस वेंचुरी. सो बेस्ड क्वेश्चन दे कैन आस्क. And the last topic is similitude based question. अभी तक नहीं आया है, but still whenever ma'am is teaching mechanical operation she will again discuss that same topic. Okay, that is your mixing part and similitude she will cover, I guess. Now up to this I hope everything is fine for everyone, flow meter and pumps etc. So go through all the equations once again for fluid mechanics. Again, rotameter based questions so far they haven't asked, but still just watch a 5 minutes animation, like 2-3 minutes animation video is there in YouTube itself for rotameter. That's enough, right? Normally rotameter based questions are less, but still orifice meter, venturi meter से बहुत सारे questions आता है, so those equations remember करना important है. Okay, yes, okay, the comment is okay. Yes, the thing is, हाँ, yes, that is your manometer questions I haven't discussed because already 2-3 बार मैंने ही manometer discuss किया है. So manometer पे equation कुछ नहीं है ना remember करने के लिए, आपको बस solve करना है ना. So that's the thing. Now, so remember, so this is our total topics. So in all topics आपको ये चीजें करना है. Properties of fluids, there are 4 topics, remember कर लो. Surface tension का 4 equation मैंने discuss नहीं किया है. प्रेशर इनसाइड अ वाटर ड्रॉपलेट, लिक्विड जेट, वो सब याद रखना है. ठीक है, एंड फ्लूइड स्टैटिक्स तीनों डिस्कस किया है. मैनोमीटर आपको आना चाहिए. ठीक है, हाउ टू सॉल्व. नाउ फ्लूइड काइनेमैटिक, एक्सेलरेशन डिस्कस्ड, कंटिन्यूटी डिस्कस्ड, दैट रिमेनिंग स्ट्रीम फंक्शन, पोटेंशियल फंक्शन, दोस थिंग्स इक्वेशन यू कैन सी. डायनामिक्स, बर्नौली इक्वेशन एप्लीकेशन, बेसिक मोमेंटम बैलेंस, सो फार दे हैवंट आस्क्ड. नाउ इंटरनल फ्लो, लैमिनर फ्लो इन पाइप सिस्टम, टर्बुलेंट फ्लो, दैट इज डन. External flow, boundary layer theory, drag force. So drag force equations you can remember. What is the equation for drag force? Drag force equation is 1/2 CF average into rho v square A. Right? CF average rho v square A. A equation कहीं पे देखा है? If you remember, your fanning friction factor equation is tau W divided by rho v square by 2. है ना. What is this tau W? Tau W क्या होता है? Tau W is actually F by A होगा ना. What is F? F is the force, shear force, जो भी force होगा, drag force. है ना. So it's the same equation, both are same. So CF average and fanning friction factors are analogous, but CF average is used in the external flow, that is friction coefficient is used in the external flow. In internal flow we use fanning friction factor, right? Both are analogous to each other. Yes. And the last topic is pumps and flow meters. Okay, so with that I'm finishing my total formula series for fluid mechanics. So tomorrow same time, mostly same time, you will have the session for the other subjects. I think IPC, I guess. So let us check. That's all. I'm finishing here. So today 8 o'clock you have a special session. Remember, you have a special session in live app. Okay, that is our basic induction program. We are starting our live classes today, actually live classes. So we will have a 3-4 days complete new session, that is basic things as a chemical engineer. What are the topics you need to know, basic calculations in chemical engineering, क्या क्या topics आपको पहले से पता होना चाहिए, so that before entering into a gate syllabus, है ना. So वो सब आज से discussion start होगा. 8 o'clock Shyam sir is taking the class. Tomorrow I will be taking the class in the live app. Okay, so from 28th we are starting a new subject, mostly fluid mechanics. I will be starting in live app. That's all. So 8 o'clock, please watch our live app. So download the Gate Academy live app, and the classes are open to everyone up to 24 to 27. Okay, so I'm finishing it here.